every math major student should know how to compute the volume of higher dimensional balls before they can graduate. Okay, so let's first fix some notations. We use B and R to denote an n-dimensional ball of radius r. And this is the definition. And hence Bn1 means n-dimensional ball of radius 1. And in short, I would just call it a unit n ball. Now here are the first few examples for the unit n balls. And here we all know that for the first 3 dimensions, the volumes are 2, pi, and 4 pi over 3 respectively. Let V and R be the volume of the n-dimensional ball of radius r. And then I claim that V and R is equal to r to the power n times Vn1. Now we first let a function g from the unit n ball to Rn be defined by gx equal to Rx. Now it is clear that g is a linear transformation. Moreover, we also notice that the image of the unit n ball under the function g is given by the n ball of radius r. And since g is a linear transformation, it is clear that g is a diffeomorphism from the unit n ball to the n-dimensional ball of radius r. And the Jacobian matrix is given by r times the identity matrix. Now by definition, the volume of the n-dimensional ball with radius r is given by the integral of the function 1 over b and r. And using the diffeomorphism g, this is equal to the image of the unit n ball. And then we can apply the change of variable formula to get this integral is equal to the integral of the absolute value of determinant g prime over the unit n ball. But we just observe that g prime is r times identity, and hence the determinant is equal to r to the power n. And now r to the power n is just a constant, and hence this integral is equal to r to the n times this integral. But this integral is exactly the same as the volume of the unit n ball. So we can now focus on finding the volume of unit n balls. Now for n equal to 1 and 2, we know that the volumes are equal to 2 and pi respectively. And then for any n bigger than or equal to 3, we will use the following method. Now by definition, the volume of the unit n ball is equal to the integral of the function 1 over the unit n ball. And then we can define this integral to be the integral of the characteristic function over the unit n ball over this n-dimensional closed rectangle. Now here note that the unit n ball is a subset of this n-dimensional closed rectangle. Now furthermore, one can show that the unit n ball is Jordan measurable, and hence the characteristic function is integrable over this closed rectangle. Now and then we decompose the n-dimensional closed rectangle into a product of 2 closed rectangles. And let's use x to denote a variable in the first rectangle, and use y to denote a variable in the second closed rectangle. Now since we have mentioned that the characteristic function chi is integrable over this rectangle, which is now written as a product of these 2 rectangles. And then we can apply the Frobenius theorem to write this integral as this iterated integral. Now let's first try to compute the inner integral. Now this means we have to find out the value of the characteristic function for different values of x in here and different values of y in here. Now let's first consider an arbitrary point y inside this 2-dimensional closed rectangle. Now there are 2 cases. Either y lies in the unit 2 ball or y does not lie in the unit 2 ball. And in this case, the norm of y is bigger than 1. And hence together with any x inside this closed rectangle, the norm of x squared plus the norm of y squared must be bigger than 1. And hence the point xy will lie outside the unit n ball, and which makes the characteristic function equal to 0. But if y is a point inside the unit 2 ball, then the norm y squared is less than or equal to 1. And now we have 2 subcases here, depending on where x is. So we have either the norm x squared is less than or equal to 1 minus norm y squared, or is strictly bigger than that. And it follows that the characteristic function at the point xy is equal to 0 if x does not lie in the n minus 2 ball of this radius, and is equal to 1 if x lies in the n minus 2 ball of this radius. Now with all this information, we can now compute the inner integral, which is this one. Now as we have just computed, if y does not lie in the unit 2 ball, then the characteristic function is equal to 0, and hence the integral is equal to 0. And if y lies in the unit 2 ball, then the characteristic function will depend on where x is, and the integral will then become the volume of the n minus 2 ball of this radius. But then don't forget we can use a formula we derived earlier, which is this formula, to change the volume of this to the volume of the n minus 2 ball of unit radius with this extra factor. Okay, now up to this point, we have already computed the inner integral, which is either equal to 0 or this value, depending on whether the point y lies in the unit 2 ball or not. Okay, we can now put the above information back into this integral, and then we will get the volume of the unit n-2 ball times the integral of this over the unit 2 ball. But now the remaining integral is nothing but a double integral, and with the help of the polar coordinates, you can apply the change of variables to compute this integral. And here is the answer, which is 2 pi over n. Okay, we can now summarize the result as the following. The volume of the unit n ball is equal to 2 pi over n times the volume of the unit n-2 ball for any n bigger than or equal to 3. And this means the value for the n dimension can be computed by using the value for the n-2 dimension. And since we already have the first two initial values, it is possible to find out all the remaining values by using this recurrence relation. Now if we consider the odd dimensional and even dimensional unit balls separately, then we'll have a general formula for the volumes. Now here is the even dimensional case. Now first of all, we'll get the volume of the 2k dimensional unit ball is equal to pi over k times the volume of the 2k minus 2 dimensional unit ball. And if we keep doing that, we'll get this ending at the volume of the 2-dimensional unit ball, which is just the area of the unit circle, and is equal to pi. And combining all the things together, we get pi to the power k over k factorial. Now according to the same principle, we will get this formula, ending at the volume of the unit 1 ball, which is equal to 2. And combining all the terms together, we will get this formula, which cannot be further simplified.